So this is your bad luck, but about half of the class was away when the course finished. You blinked and it was over. So, everything I did in the whole semester culminates in this formula, which is called a trace formula. I call it classical. And it's totally amazing. After all the, pondering how the topology of the space works, what a stability of local orbits, etc., thinking of Perron-Frobenius operators, density evolution operators, all kinds of fancy stuff. Bingo. A beautiful, simple formula, whose meaning is that on the left-hand side, the world is full of periodic orbits. If we have an ergodic system, an unstable system, and they have some complicated topology in the state space. So here is one of them. And they all live in state space. And if things are nice, the state spaces are densely filled out. And so in every neighborhood, open neighborhood, there are periodic points belonging to periodic orbits. And the idea of this thing was, when they're unstable, this periodic, actually also when they're stable, but when almost always periodic orbits are isolated, unless they belong to continuous families. And that we took care of by quotienting spatial symmetries. So they're almost always isolated. And why they're isolated? Because they're hyperbolic, meaning that anybody in neighborhood, is being shoved away. So it's impossible to have a recurrence in a close neighborhood because things get sucked in, thrown away. So each periodic orbit of some period doesn't have a neighbor of the similar period, but it might be much longer periodic orbit that went someplace and came back to their neighborhood. But for a given time, we can put a little tube around each orbit. So I can write a little tube. So there's just an open neighborhood of this periodic orbit, which has a property that there is nobody else in this little tube who is exactly recurrent. And then the way that this was evaluated was to say, when I look at this tube, it has a natural coordinate system. So when I blow it up a little bit, and the easiest is to put a Poincaré section. So this tube cuts the Poincaré section here. Inside there is a periodic orbit, which on Poincaré section has a periodic point. And it's totally natural to construct coordinates, one of them which is parallel. So it's coordinate that goes along the tube, and it's a cyclic one because the periodic orbit itself is finite period. So if I put some coordinate here, and then the rest, we'll call it transverse. And for periodic orbit in arbitrary dimension, you can always decompose this locally. And the way then we did these calculations, we showed that integration, and I haven't actually done it, but it's in the book, I've done it only for the maps. I've done it for transverse part. But for longitudinal part, you show that morally, the length of this tube is actually its period. So this thing that used to be counting how many periodic points we had when we were computing trace maps of transition matrices, very simple finite dimensional matrices, there's always number of points because each periodic point contributed to trace. In continuum, it just becomes a continuum variable, and dimensionally it turns out to be time. So just this is the length. And then the transverse one is the one that we did when you blinked last Thursday. But basically, in transverse direction, what happens, you have to integrate Perron-Frobenius operator, which says I have to integrate transverse part of the delta function of starting at x and ending at x being on periodic point. So this is our transverse coordinates. And that this gives me 1, d minus 1 dimensional. This one is d minus 1 dimensional. And this part gives me the matrix intersections, a transverse matrix. And I'm using a new letter. In mathematics, they have something called monodromy. It's from the Greek dromos, the stadium, and mono, meaning once. So it means you go once around the play field or something. So that's monodromy. And this one is hyperbolic because we have removed the marginal direction here. So this one has eigenvalues which are either larger or smaller than 1. And then integrating high-dimensional Dirac delta function always produces a Jacobian. You have to go into coordinates where this vanishes, and that's this Jacobian. That's all. And then our evolution operator had 2 pieces. One was we computed something on periodic orbit because we were developing field averaging. And this is integrated observable on the periodic orbit. And then there was a cost which came from Laplace function, Laplace transform. And since last Thursday I've suffered so many anxieties, I've recorded a handwritten derivation of why there is a Laplace transform. It's on the web. So that's it. So on the left-hand side, we had this. Where did this come from? This came from a Laplace transform of, we wrote the evolution operator at time t as evolution operator for infinitesimal time integrated. So you can think in quantum mechanics this is like Hamiltonian. It's not quite right. And then Laplace transform of this gave us 1 over S, where S is a Laplace transform variable. It's dual to time, just like energy is dual to time, minus operator. So Laplace transform gave us a resolvent. And I'm willing to discuss all these things after you have watched the videos. And if you don't understand something, put it on Piazza. I will dutifully answer to all questions. But this is testing. Imagine that you're part of 40,000 people who will no doubt want to take a course like this some later time. And trace of this object is the sum of the eigenvalues of the operator. So that's the left-hand side. So what this means is that on the right-hand side, we look at our world, and we divide it in little local neighborhoods, and on each one of them, we have a formula to compute contribution of recurrent solution. So it's because of this trace formula that we are forced to look at periodic orbits. It's hard, I don't enjoy it, but I don't think we have any choice. This is the natural invariant set. Everything here, see, this Jacobian is as we showed very early in the course, it's invariant under all smooth coordinate transformation. So it doesn't matter whether you do it in Marburg or in Kyoto, this determinant will always be the same, even though the matrix might look different. The eigenvalue is always the same. Periodic orbits are indestructible. They're topological invariants. So whoever finds a periodic orbit any place, it'll exist in any other realization, any other coordinate version. If you agree that we are, measuring an observable, we all get the same answer. It's very simple. You just integrate whatever you're looking on the trajectory. So it's very simple to compute this part. We'll all agree more or less what the period is. That might be open to discussion if you redefine the time, but then you'll have to think about what it means on the left-hand side as well, because it shows up on the left-hand side. So right-hand side is local. But the left-hand side is global, because we are studying the eigenfunctions of this operator that acts on the whole world, on the whole M. So what the left-hand side is doing, and that's very hard to draw, but we're defining functions and finding an eigenfunction basis because it's a linear operator. So there are functions, and they're called phi alpha, the eigenfunctions, just like in quantum mechanics, except they might, this is a more difficult subject than quantum mechanics. So you've learned Fourier transforms. You've learned that you can think about things either in terms of waves on a line, or you can think about in terms of points on a line, and that's what Fourier transforms do. And this is the most general form of what such duality is for a nonlinear system. Fourier transforms are just a theory of what happens on a circle. This is theory of what happens on any manifold, where we only assumed some differentiability, some smoothness, and in physics we assume lots of smoothness. And in any dimension, only thing we are requiring is determinism. We're requiring that our solutions have unique future, if not the past. Now, a week ago or 2 weeks ago, I showed that if I know these eigenvalues, I can compute averages, if I can take derivatives of these eigenvalues. And it's something that might be familiar from statistical mechanics. It's the same machinery that one has in statistical mechanics. So now we have kind of unspeakable related to unthinkable. This is unspeakable because we don't really know how to compute these eigenfunctions and eigenvalues. It's rather difficult. So we know how to solve these problems in one dimension and two on a computer. We can sometimes do a reasonably good job in one dimension looking at some unimodal map. And the reason why we can do this is that even if you try to do, so maybe I'll put it in Chaos Book, right now it's not there. If you try to find the most important of all eigenfunctions is the 0 one, which is called natural measure. So phi 0 of O of x is called natural measure. So this is what you obtain by noisy computer iterations, I mean imperfect computer iteration. If you just look at long-time dynamics, you find that in some regions you're more likely to be, in some regions less, and most of the space not at all. Because usually these attracting sets where dynamics settles in at long time are smaller than the embedding space itself. And even when you do it for some totally simple, so of course in Chaos Book I have one example where you can analytically compute this measure and it equals 1. But that's the only one example. That's called ULA map, and you can, well no, it's actually not 1, but it's, tent map has 1 ULA map. But if you just take any bimodal map, unimodal map, just with 2 branches, which is not parabola, and you start numerically computing this rho 0, the natural measure. So this is defined on interval 0, 1. So what you can do, you can just start someplace and you can iterate. You start someplace, you iterate, go someplace else. And as you do this, you're filling points on unit interval and you can box them. You can do this. It's very cheap to do this for a million times or whatever. And you'll get something totally horrible. You'll find that it's singular every place. And if you blow it up, it'll be singular. It has very good reasons to be singular, so it's not surprising. So this thing that mathematicians feel totally comfortable with because they say, oh, the measure is continuous on unstable attractor, we prove it, there is axiom, blah, blah, blah. That's because they don't have to work. If you actually do this thing, it's just horrifying. So what happened to that thing in the trace formula? How did we, the whole point of all Chaos Book is that you don't do this, because you can do this and it doesn't make sense and just crazy things to do. So how did the trace formula circumvent this? What the trace formula says is that dynamics has some simple law. So as you'll see, these contributions will be organized by shortest period to longer and longer. I'll explain why, but basically this volume is shrinking exponentially. So longer periodic orbit exponentially small compared to the short ones. And in short time, we have very simple dynamics. In short time, if you start with a smooth function, you get another smooth function. This you get only at infinite time, this incredibly crazy thing. So what periodic orbit theory says, look, the way I've constructed this, at long time it looks complicated, but I've done this by doing the same thing over and over. Totally boring, repetitive motion. I do this, I apply this map, I apply this map, I apply this map. It's totally innocent in any single iteration. And by using this finite periodic orbits, I have a good description of neighborhoods here. And then it turns out that longer solutions, and that's the point of today's lecture, I'll show you don't actually use trace map, you use the determinant, not the trace formula to compute things, have a property that these short repetitive motions are dominant. That's what we did when we look at these finite dimensional transition matrices. We define fundamental part of the cycle expansion, things that describe qualitatively the most important thing that happened in dynamics. And the rest turn out to be super exponentially small corrections. So by understanding topology, this unspeakable formula, which has infinitely many prime orbits, each one of them repeated infinitely many times. So there's no way in the world you can compute this. Same thing on the left-hand side. No way in the world you'll compute infinitely many eigenfunctions of this. We can only do it for harmonic oscillator analytically, and that's the end in quantum mechanics. So there is, and here there's some examples where I can do it, but they're similarly silly. So that's the meaning of trace formula, and it turns out that this trace formula is something that's, it's all over physics and mathematics. It's kind of every place. It has different names, so it might be called Zeta function or something, or some kind of Zeta function, etc. So the story, the history is just great. It starts with three things where people don't talk to each other, period, and they have no reason to talk to each other. So one beginning is Euler, who did it all, but it's called Riemann zeta function, because Riemann made a conjecture about it, made a hypothesis about the zeros of Riemann zeta function. So there is a part that has to do with number theory and counting primes. So, what do we care about counting primes? I mean, we are happy to count to 3 in physics. Why should we care about counting primes? And then there is a very, very long history, because it turns out it's the big outstanding problem in mathematics to prove Riemann conjecture. And it's not a silly problem, because it's extremely fruitful problem. I mean, lots of good theory, lots of good mathematics has come out of it. I mean, it's not, amazing amount of good mathematics. And one version that's very close to what we do in dynamical systems is a mathematician called Selberg in Trondheim during the war, 1943, etc. During that war. He had lots of time. People in Trondheim, turns out, have lots of time to think, sit and think, because the weather is incredible most of the year. So he decided, if I can solve the zeta function, which is an issue about lattice of integers in one dimension, let me do it on a lattice in 2 dimensions. And then he did something called Selberg zeta function, which is very inspirational for us. Which you see studied dynamics on 2-dimensional discrete lattices. And he proved the equivalent of Riemann conjecture. Now we don't know still how to prove that one, but the fact that he proved it in 2-dimensional case is extremely fruitful. It's very closely connected to quantum chaos. So what happens in the quantum mechanics of classically chaotic systems. So that's one example. So there's a huge tree of knowledge coming this way. Then there are people like Poincaré and Birkhoff and some Russians and this and that. And it kind of comes to, in modern times, come to David Rouel, who is a Belgian mathematician working in Paris. And he wrote a zeta function, which is sort of, I'll derive it today, which is a kind of approximation to this thing. And that was done thinking about foundations of statistical mechanics. So that's a thing about what happens when you're trying to make statements about entropy, about this and that in statistical mechanics. And then there's a third branch, which is quantum mechanics. So people who do quantum mechanics couldn't care less about people who, make satellites and stuff, because that's for engineers. They don't care about classical mechanics. They do quantum mechanics. So there is a man called Martin Gutzwiller, who comes from Basel. He's Swiss, and he collects, in Basel people collect all books. So he collects science books, like second edition of Principia or something, and some expensive books like that. And as his hobby, he does celestial mechanics, but he's a quantum mechanician. He worked for IBM to study properties of gallium and silicon because people have to make semiconductors. And he realized that he can generalize Bohr-Sommerfeld quantization and use WKB to something that's called Gutzwiller trace formula. So these three groups of people don't talk to each other, and they still don't talk to each other. I mean, so they're kind of very respectful. Ruel is convinced, I know them all, they're living ones. So Ruel is convinced that what Gutzwiller has done is unrelated to him, and it's some kind of fuzzy thing physicists do. It's not rigorous. Gutzwiller is convinced what Ruel did has no relation to what he did, etc. But he likes Selberg, so he thinks, etc. And mathematicians, of course, don't care. They do whatever they do. The amazing Zeta function guy will show up on Thursday. There's a man called Zagier, who is very quietly announced in math seminars. Now, when I was an undergraduate, I, got my undergraduate degree at MIT, but this guy got his PhD, and I think he was younger than me. So he just kind of went through the MIT like meteorite. And he's a brilliant mathematician, and he has his own zeta functions, which are totally amazing. The zeta functions, they're very important for modular domain, etc. So these subjects are very much alive. And I have to emphasize that this is exact. The only issues in this trace formulas are Gutzwiller is semi-classical. It's described in a part of the book that I can't lecture about at Georgia Tech because we don't have time for that kind of stuff, but it's only leading order in H. In H bar. But in quantum mechanics, it tends to be often very good. And Selberg zeta is exact, but it's number theoretical in the sense that you learn everything about Selberg zeta function and you cannot apply it to anything else except integer lattices that Selberg studied. It doesn't carry over to anything. This thing is supposed to be true for any dynamical systems where you're given equations of motion. And, but. So then there is a whole subject which is Ruel Baladi, a young French, well actually Swiss mathematician working in Paris. Vivian Baladi, who, knock off rigorous things you can say about the system. And the rigorous things, the problem with this rigorous thing is that, for example, they depend on symbolic dynamics, and we can only control it in one dimension. So even in 2 dimensions, we do not know how to do it. So, so there are rigorous results, etc., but they're limited because we don't know how to be rigorous enough. Now, my attitude is pragmatic. This formula is exact. It's totally insane formula because it assumes that you can parse the state system infinitely well to infinite time, which is not kind of crazy. So neither sum is infinite. We only take finite number of periodic orbits. We have to only take finite number of repeats. And we do it, justification being that we need a finite precision answer. And the moment you say this, you have coarse partitioning. You don't have to compute everything. It turns out mopping up is non-trivial. So the main thing was more or less in place in the beginning of the 70s, maybe 80s. But people who derived this formula were mathematically inclined originally. And actually that doesn't even look like this. You can identify something looking back that looks somewhat like this. So they didn't actually think that you could compute with this stuff. It was just beautiful mathematics. And it turns out that in chaotic systems, this is the way to compute. This is a computational scheme. This is not just a beautiful piece of mathematics. And the idea is that if I really only want to make predictions, it means I want to produce numbers. I want to tell you, the mean diffusion in some ocean which has turbulent motion is given by some number. For example, a piece of junk floats on average 50 miles per day, but it does the Brownian motion. So that kind of thing can be predicted, and I'll finish, I'll use it as application of all this technology. Transport properties can be computed using this methodology. Now, mopping up is the first thing, is that this is a beautiful formula, but it doesn't turn out to be very good in practice. And in kind of trivial way. I mean, just that the way you actually compute eigenvalues, in practice there are two ways. The one that seems to be most efficient, so if you click on your MATLAB and something happens, somebody's done thinking for you, what they do is they compute eigenfunctions and eigenvalues. And that seems to be numerically best, providing system is small enough, with number of caveats. But the other way that we compute eigenvalues, we look at characteristic determinant. We did this for finite dimensional matrices, and we find zeros of that determinant. Now, there might not be the numerically most efficient way of finding the zeros, but it has advantage that everything in that calculation will be of this form, which is invariant form. So, it'll not depend. Whenever we find eigenfunctions, eigenvectors, we have to have a basis to compute. And I just happen to know that eigenfunctions in this problem are horrible. So I'm not very hopeful that this is a good way to compute them, but maybe I'm wrong. And that's about it. You would never compute eigenvalues by looking at traces. Just don't do this. Now, you'll see why is that. And you'll have a very beautiful geometrical meaning. And geometrical meaning of using determinants. Determinants will have traces appearing with minus sign. In dynamical system theory, on the right-hand side, trace means a periodic orbit. So weights of periodic orbits will show up as relative minus signs. And there is a deep reason for that. They shadow each other, and then they immensely improve convergence of the theory. Now, the main identity is the usual one, is that a trace of the log of a matrix is log of determinant of a matrix. And now, if you write this out and take exponent of both sides, you find that determinant of 1 minus our evolution operator, and because people justly didn't like the z, didn't like generating functions, a radical haircut. I tried to explain that you can interpret the z as some kind of probability. So if you watch my video, I hope I'll convince you why. It's kind of curious you like Laplace transforms more. It's just power in the declination, because Laplace transfer is a more difficult concept than summing polynomials, but you're used to it more. Anyway, it says that that is e to the trace of a logarithm of 1 minus z lambda. Now, z is now a very useful handle. The operator itself, if you really care about such thing, can be bounded in some way. So if z is sufficiently small, this makes sense. This can be expanded as a Taylor series in z. So then we use a famous identity that says logarithm is minus sum k equals r, n equals 1 to infinity. Instead of factorial for logarithm, you have 1 over n here. And then you get this thing to the nth power. And this is a matrix model. It's an operator, so you get a trace of the logarithm of the matrix. But this object we computed. It's here. We have that object. So we know that the way we want to write this object is we want to write it as e to the minus n equals 1. And then we had this thing that we can write this as, I'm doing this for discrete time first, but the continuous time is very similar. All p, each one of them had np periodic points, and then all repeats r equals 1 to infinity. So I'm just rewriting this n in the form trace of L computed on periodic orbit. So because they're isolated, I can do this locally to the np times r. But this only contributes cnp times r if n equals np times r. So only terms in this sum, so this is just this thing rewritten. Only terms in that sum that contribute are the ones in which n is factored in a small, shorter prime cycle and its repeat. So that's just identity. We did this number of times. But we have this sum over n's, which gets rid of this delta function. So this becomes e to the minus sum over p and p. And then divided by n. Okay, so there was an n here, right? So np divided by n equals, because of this Kronecker delta function, and I'm going off the camera. Np divided by n is np divided by np times r, because we only allow the repeats of a shorter cycle, so this cancels. So we get, instead of n, we get 1 over r. R goes from 1 to infinity. And this thing we computed, so this thing is called determinant 1 minus, we picked up a Jacobian here of the prime orbit. If we do it in a map, we just get this If you don't do it in the map, you get the other thing, but the form is the same. Then it's e to the minus, well, to the our little parameter that we'll use to manipulate series, because we will have to take derivatives of our eigenvalue with respect to this parameter, minus s tp. So this is computed on periodic orbits, and for repeat, it's repeated r times. And that's it. And what is a determinant? Oh, I see. This is stupid Z and P R, if you want. So the determinant is 1 minus, well, it's just product of the eigenvalues, right? Now, on this thing you can rightly object. I think you should object, because this is a determinant of an operator on infinite space, so we really have to think about how it's defined, and it's actually defined exactly in this way. So determinants of operators on infinite dimensional space, the so-called trace class, are defined in terms of traces. So if these things are convergent, then the left-hand side is convergent. Now, for some reason, my colleagues in literature claim that this is a clever resummation. I never understood why determinant is meant to be a clever resummation. That's what it is. Determinant is expressed in terms of traces, and we have expression for traces. And at this point, everything I'm saying is okay for you for finite matrices. If you seriously, follow the counting chapter, our discussion there, all these manipulations are legitimate. Now, where they're legitimate for infinite dimensional spaces is a non-trivial thing. So one has to prove that these formulas make sense in this very general context of applying them, let's say, to fluid dynamics or cardiac dynamics or God knows what. And the mathematical status is that we can prove this for some idealized flows, which are non-trivial, So there is a group in math right now that's going through this every week, through the math part of this stuff. But in working with these formulas, we get very good intuition where are the pitfalls, where the things could be wrong, etc. Some pieces of this have been worked out, but we will use this from now on, and that will be the point of the next lecture. I'm sorry, the next lecture happens in the following way. If you don't come here, I don't mind. It's only video. I'm in a NSF panel, mathematical physics panel, which is the orphan child of sciences in the United States. It has like money for 3 people, and it has 100 very good people applying. So we will ponder how to give money to very few people, of many excellent people who are applying, and I can't show up in any form on Thursday because I'm in this stupid meeting. Not stupid meeting, it's an important meeting. It's a good organization, I support it. It's very efficient. It's not corrupt, it's amazing. National Science Foundation. My officer, are you hearing this? No. That's it. So now, we have come to the point of this. You didn't care about what I did for months. You wonder, why the hell are we doing this? It didn't make sense to you, even though for me it's like, total one red line going through. It culminates in a beautiful formula which you can understand, and you can go to next to and write it down again because it makes total sense. It just says, look at the prime cycles and their repeats, and each one of them has a tube, and thickness of the tube has to do with Jacobian, and the length of the tube has to do with this. And on it, the long period should be less important, so there is minus, variable dual to time, saying those guys are less important. And I compute some average on it, and that's it. And Predak says, well, that's nice, but actually when you use this formula, compute this instead, and find zeros of it. So, okay, so now I want to only do one thing with this amazing formula right now. On Thursday, I'll show you how you actually compute with this formula. But here we'll do a physics thing. It turns out it doesn't have to be done as a physics thing, but it's easy to understand. It's actually an exact formula that one can get, but here we go. So what's the determinant of 1 minus MP? The first repeat of this guy. R is very easy to put in. Well, that's just the product of eigenvalues, which I'll write in the following way. I write them as expanding eigenvalues. So 1 minus lambda p expanding, and 1 minus lambda p contracting, expand, contracting. And the number of expanding plus number of contracting plus 1, because there is one marginal direction along that we have eliminated. That's the whole dimensionality of the space. So maybe I should call this these. So, unstable manifold, stable manifold. Now we want to have an absolute value of this guy, so we put absolute value around this. These guys are smaller than 1 in magnitude. Doesn't matter, very complex. So I can only put absolute value here. And now it's natural to pull out this product, LP E over expanding, and write times the product expanding of 1 minus 1 over LPE. Now this is smaller than 1, so the absolute value just comes here. And early in the course, I defined this to be instability of an orbit, the product of all unstable eigenvalues. That was the important stuff. And now it's being modified by corrections, which are exponentially small for long orbits. Because for long orbits, multiplier goes exponentially with the period, and this. So these are corrections. So I just divided multipliers of the matrix or eigenvalues of matrix into the ones that are larger than 1 in magnitude, smaller than 1. Then I've decided to pull out this larger than 1 factor collected, and the correction is smaller than 1 term. And now we do a physics thing, which we say, let's just drop this, guys. So that's what you do for rev letters. And then what happens, and now I'll use a different letter. You get a formula that says that this is e to the minus sum over periodic orbits. LP to the power r, because all the eigenvalues get raised to the power if I put r's here. So these are the repeat number. over C and C to the np times r, e to this thing times r. So everybody is raised to power r. So now I can use my definition of expansion of logarithm. So let me call Tp, let me call it z to the np, e to the, all that stuff, ap minus, but not repeated just once, minus s to the p divided by rp. So this now just becomes, plus sum over p. I can sum this r, that's definition of logarithm, so it's logarithm of 1 minus Tp. And if I have something here that's a product, an exponent of logarithm is it, it's 1 minus Tp. So the zeta function that I introduced originally for counting, topological zeta function, is actually an approximation to the determinant. And it's an approximation which should be good, and you can prove it for the leading eigenvalue. You're interested in the leading eigenvalue here, this leading eigenvalue of your operator, which says that longer cycles have some very small exponential corrections. I can drop them. So now this formula is extremely easy to use. It's not the best one, but it's pedagogically the easiest one to learn how to use the stuff. When you actually compute and you have control over, if you have found 3 periodic orbits and you don't know, you've gone fishing, you came back with few orbits, you don't know what they are, what are you missing, etc., then all this stuff is useless because you have no control. But if you got into a situation where you know all the short ones and you know how to make sure that you pick up the next longer ones, then this starts working. So you really need to understand topology of the problem before this starts working. But you get this amazing formula. It says I only have to compute all prime cycles, only, infinitely many of them. But then we already saw that we can arrange it as a power series and truncate and have shadowing, etc. So that's what I'll exploit next time. Okay, then actually there's something I would like to do. I mean, it probably would be human to stop now, right? Because you could torture me for a while and maybe you'll understand something better together. But I want to just say one thing which I think is relatively easy to understand. And that's about meaning of this kind of formula. And it's one of those things about the perils of moving to infinite dimensions. See, what we have done is we started for Lorentz system in 3 dimensions, for fluid dynamics, 100,000 dimensions, but it started in finite dimensional dynamics. And then I suddenly upped the ante. I turned it into a linear problem on infinite dimensional space. And that is a price to pay. It's not. So the dangerous things can happen quite easily. So here is one totally dangerous, simple thing. So let's take a very simple system. The system has 2 branches. And the slope is L0, which is L positive, and this slope is L1, which is negative slope, so it's minus L, lambda. So these are slopes. So map is very simple. It's a linear map, but it has two pieces, which makes it a factor nonlinear. And now we are already used to the idea that maybe sometimes it's good to look at exponent. So we can write e to the exponent. So this says if I have some area on the unit interval, in one iteration of the map will be blown up by this number larger than 1. Or you can say there is a rate of expansion per unit time, where unit time is a step. So this is a rate. And in crudest form, this is called the Lyapunov exponent. So basically it says that if I have something, it moves around here, but it's getting stretched by the same number per every unit. So per unit time, I'll get lambda in this dynamical system. So all errors are growing at the same rate. Very simple system. For that case, I've actually worked this out for you already. So we found that the expansion of this thing was 1 minus z times 1 over Lyapunov. This whole determinant is now being replaced. Remember, we replaced determinant of 1 minus m. We replaced it simply by product of expanding volume. Justification being that if this is larger than 1, and for large R, it totally overwhelms this 1. So that's for this branch. Remember, this was a simplest dynamical system where we had two nodes and we moved either this way or that way. We had two contributions, and now they happen to be the same in this case. So this is 1 minus so this thing I decided to call remember, we also have a convention that either we write it as z or we write z as e to the s, where s is expansion in 1 unit of time. So I can write this as e to the minus s. Now these guys are the same, so I can write this as plus h, where h is logarithm of 2. And then each one of these guys I can write as minus Lyapunov. So are you with me? These two things are the same. That gives me 2z. I decide to write e as some letter h, where h is a logarithm of 2. So that takes care of the number of possible paths. That's called topological entropy. This is the number of ways I can go per unit time. Then each one of them has either z, but I decide to write this in exponent, just to put everything into an exponent. So this is our parameter, and our game is to find values of z for which this vanishes, because these are the eigenvalues of the original operator. Now, here it's very simple, just a linear function. And then each solution, now it turns out in this simple system, it's enough to find the two fixed points and their slopes. So this is, and they each have a weight. The weight of periodic orbit is 1 over the product of unstable eigenvalues z to the length of periodic orbit. And I will ignore, I'm not averaging anything, so that's it. So there are two of them, 2 or 1, but they have the same absolute value expansion rate. So that's what this part is. And I decide to write lambda as e to the rate. Right? Now to find the eigenvalue, I need to set this equal to 0, which tells me that S equals h minus lambda. Pavel didn't show up. He was complaining about escape rate. So this thing here, the leading eigenvalue for an open system is called escape rate. And I think that's what you did this week as a problem set, if I'm not mistaken. So this is escape rate. And probably got the signs right, so this should be plus. Yeah. And with escape rate, this is called a Lyapunov exponent. And this thing is called Kolmogorov entropy. The link. So what this formula says for this very long map, that the escape rate is proportional to the expansion rate. What it means is if I take a ball and I stretch it, then in my volume I'll get less if it's more unstable. So it's proportional to the expansion rate. But I have two branches, which kind of means in 3-disk problem what happens is I'll leave one disk and I think I'm going away because I have my Lyapunov exponent, but I can actually hit the 2 other disks, in which case I'm backscattered. So this is the number of ways in which I'm kept in a system. And the escape rate, and in this case, this is exact, but this is actually a theorem with somebody's name attached to it. In general ergodic theory, escape rate is the difference between local expansion, average local expansion, which is this Lyapunov exponent, and entropy, the number of ways I can go back. So that's a correct interpretation of zeta function. Turns out to be correct in general. You can make it into theorem, but certainly for these linear systems, that's what this zeta function means. It says, I'm computing leading eigenvalue of that eigenfunction. If the thing is decaying, it means I'm leaking out. And rate of decay is given by the leading eigenvalue. If the system is contained, leading eigenvalue will be 0, but otherwise it will be less. And all other ones are negative because any distribution decays toward the limiting one. And that's related to expansion rate minus the entropy minus the number of ways I stay in the system. Here is identity, but it's generally very true. So this is the correct way to think of zeta function. But here is a totally logical way to think. It says, so here I can write this explicitly. I can write this as 1 minus the weight of the first orbit is z, it's of length 1, divided by lambda 0, 1 minus z over, so these are my first 2 prime orbits, length 1, fixed points if you wish. Then there is length 2, and I happen to know there is only one. I happen to know there is only one cycle that bounces between the 2 prime cycle, And then there's 1, and this is of length 2, 1 minus z3 lambda. And I happen to know there are 2 of those, 0, 0, 1, and so on. So now it's obvious. I want to find zeros. Well, 1, 0 is if I take z equals lambda 0. The other 0, is double in this particular case. The other 0 if I find z square equals lambda 0, 1, which in this case happens to be our lambda square, etc. But anyway, I find that the eigenvalue is just the expansion rate. There is no h. And that's totally wrong. So if you have an infinite product, the zeros of that infinite product are not the zeros of the function on left-hand side, and the way you do this more carefully, just like you do it for a Riemann zeta function. There's also the same formula exists for Riemann zeta function, and you understand that the zeros of zeta functions are not logarithms of primes, prime numbers, which are just prime numbers in the case. No, they're totally non-trivial things on the real axis. And the way you do this is that on the infinite dimensional space, it's really defined by trace formula, and then you analytically continue in Z, and you make sure it's convergent someplace, and this product is not convergent as it stands, etc. So, that's kind of totally elementary error you could make by deriving these formulas as a physicist and not worrying about convergence. It's really important that, what's convergent. So that's why I emphasize this determinant-trace relationship, because that carries off to infinite dimensions. But these kind of products of eigenvalues don't necessarily. Questions? I don't understand how anybody would understand this without what we did up till now. Otherwise, I would not. I would do it in the first week. I could have done it in the first week. It's like teaching quantum mechanics. You just write Schrodinger equation, write spectrum, and you say, ah. But I think here you have a chance of understanding. This is classical. You can understand everything. So, do you have anything to say, or you just?
Is there an intuitive reason why equilibria don't show up in this?
It's an extremely good question. In the Boy Scout version of the book, which we can share, but the vulgar people outside Georgia Tech and outside the group of collaborators cannot, I have a formula for equilibria, and I don't know what to do with this. So I'll hand it to anybody who wants to. Just check out the Chaos book and you can read it. So I have the formula, and I don't know what it does. So my intuitive idea is that we're interested in dynamics. So we're interested in averaging, and equilibria don't move. So they're very important.
These don't move either.
Well, they're invariant set, but they encode time evolution. See, each periodic orbit is an invariant set, but it's encoding the time evolution on the set. So, we know that they move because they explore the turbulent regimes of our problems. So, we can literally see what they do, because we can see that they're close, they never, what you see in turbulence, you see in individual periodic orbits. They capture that. So they capture dynamics. So if you have a system which is, for us, boring, but it's, often the most interesting thing. So for example, let's call statistical physics. When you go to one fixed point, phases is blah, 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 then equilibrium is very important, because you just compute the average by evaluating at equilibrium, and that's it, you're done. No need to average over it. But if you have dynamics, I haven't found a good way of using the part of the trace formula that comes from equilibrium. So in this thing that I did on the web for you and in the class before, but in the Laplace transform, this quantity, I fuzzed about epsilon equals 0. I made it slightly positive. And also, when I derive this determinant, when I do it a little more seriously, I have actually a ratio to determinants in which epsilon 0 cancels out. So I regularize them. So I don't see the equilibria. They're seen indirectly because the shape, whenever trajectory comes close to equilibrium, it picks up average properties of equilibrium. So if it's a complex equilibrium, the velocity it moves around is given by the complex part. And so they're indirectly very important. But in cases I'm familiar with, and Lorentz is the simplest example, equilibria are there. They play a geometric role because they shape the whole thing, but you never visit them. You never visit the ones that you just can come close to, and you don't even visit the one that you know that you're there because you have no probability of getting there. So I don't know. This is a very important question. I would like us to be able to use the information about equilibrium because now we use it indirectly. We take periodic orbit that comes to equilibrium and goes away. Then the one that circles it once and comes back, circles it twice and comes back. And so we use that information. So it seems like stupid. Shouldn't we just use the equilibrium itself instead of circling it 7 times? And for hyperbolic systems, it looks like you don't want to do that. Your equilibria are kind of cut out from the important dynamics. They're not part of the strange attractor. They're not connected. But that's totally open to discussion because we know the unstable manifold are connected. It's just that it's not obvious that a stable manifold are connected. It's not obvious you can come to them, but you know that you can leave them and go ergodic. So they don't seem to be part of recurrent sets, but I might be wrong. There might be very important examples where they are.
They appear to be very important for the 2D turbulence on the 3rd floor.
So it's also true of 3D turbulence, and it works in this crude way that if you look at pictures, so that's what people do who work in plumbing, they take snapshots of the numerical simulations. The human eye cannot discern the difference between an equilibrium traveling wave or a near passage to it. So at the level of 10%, 5%, 10%, etc., estimates of dynamics, these equilibria are very helpful. They give you pretty good guesses because it turns out these equilibria, are pretty complicated. So they capture some very complicated, entwined states of fluids and cardiac dynamics and whatever. So they're good at that level. Then when you look closely, and for that you have to go to state space, it turns out they're not part of the game. So that's, we see this in Navier-Stokes. So we use equilibria to kind of usher, put a cage around, you use the stable unstable manifolds to put a cage around turbulent behavior. So you can see they're very important because, you seem to be just staying where they tell it to stay. They confine the stuff. But all the averages are computed on the time-dependent solutions on periodic orbit and relative periodic orbits. So I agree they are qualitatively important until you start looking in detail. So I can give good example. For example, Gutzwiller, who invented chaos, one of the people who invented the serial periodic orbits in context of quantum mechanics, but calculations are classical, the WKB calculations. He first discovered that there is only one unstable periodic orbit. And the way he did this is he had a problem which in certain limit was Keplerian motion. So it was just motion of electron around a molecule in the lattice. So that's a Keplerian problem. And then when you put it in a crystal, it becomes anisotropic. So effective mass in various directions is different. So then what he did is he took solutions of Kepler motions, which are ellipses, and then he made it slowly anisotropic, and he found that there's one orbit that stayed. One ellipse was not anymore an ellipse, but it was a solution. And he published a paper, and he got the conductivity of germanium and silicon to 5%, which is pretty good. But periodic orbit theory does this to 10 to the minus 6. And you care about this when you're looking at spectra of helium, for example. 5% is not good enough if you can measure it to the 13 significant digits or something. So you really care about this stuff. So it's the same in fluid dynamics. They're very important. It just, you can use Rossler attractor equilibrium, get some estimate for typical times and typical values of things on the attractor, but you're actually never there. You're someplace else. So more accurate calculation requires this. Now, I hope you're blown away, because you should be. It's all trivial stuff, step by step, but unlike quantum mechanics, I never assumed anything. I didn't do Schrodinger to you. Everything that's done in this course you understand. And here we are. It's not obvious after a while. But the claim is this is the best way. If you have turbulent, chaotic dynamic behavior, which is dominated by deterministic laws of motion, and you want to understand what happens in times longer than Lyapunov times, what are the long time predictions, this is how you do it. It's the only theory, there's no alternative theory. If you find other silly formulas in physics of letters, they are wrong. This is it. I'm mentioning this because there was a graduate student at an institution not far from here who was not very good in learning, so he didn't want to study this. So he wrote some silly formula and published in Physics of Letters, and people use it because it's very easy to use. But it's totally wrong. But it's easy to use, so people use it. I'm sorry, but it's a good thing. Okay, sorry, I ran over. Have I ran over?
No, he's still 20